So 12.1, part 2. And I'm just going to say more vector value functions. So I don't know what happened. This happened kind of recently, where my E's end up looking like they're backwards, and I really tried to
That's a real problem.
to continue that, so that this comes down and so it looked more like an E. But I've kind of reconciled myself to the fact that my E's are backwards now. When I was in middle school, we had to write in cursive, and my English teacher in middle school told me, he said, just print, don't write in cursive anymore. And I've never written in cursive since. It was such a relief not to have to write in cursive. All right. So the first thing, what I want to do is just go through a couple of examples of how we might of sketching curves from a vector value function, and coming up with vector value functions for various kinds of curves. That's really what our lesson is today. So we're going to figure out sketching curves. So we have this vector value function. So let's say that we have r of t is 3 sine ti plus 4 tj plus 5 cosine t ki. And we want to sketch this. We want to sketch the curve. And hopefully, by the end of the semester, hopefully before, we can look at something like this and just, without having to do a lot of analyzing, have an idea of what this curve looks like. So, any ideas of how we're going to start? Any suggestions?
We can look at traces in each of the planes.
Look at the traces in each of the planes. So looking at this vector value function, this 3 sine ti, 4 tj, 5 cosine tk, what's going to be the easiest plane to analyze initially? XZ. So in the XZ plane, we have x equals 3 sine t, and z equals 5 cosine t. So what kind of relationship can we come up with for x and z here? An ellipse. Okay, so this is going to be an ellipse. So let's write a rectangular equation for this curve using x and z. What would be our rectangular equation? I'll get us started. X squared over 9 plus z squared over 25 equals 1. So there's our ellipse in the XZ plane. Now thinking in 3 dimensions, what is this surface going to be in 3 dimensions? Our trace in the XZ plane is an ellipse. What can y be? Y can take on any value. So what is this? Someone said it. We have an ellipse, but the surface is a cylinder. So we have one missing coordinate. We said when we have one of our basic kinds of surfaces, when we had one missing coordinate, we get a cylindrical surface. So this is an elliptical cylinder. along the y-axis. So our curve is going to lie on that. Our curve is going to lie on that cylinder. So let's sketch that cylinder. Our curve is going to lie along. Is going to be on this elliptical cylinder. So here are our coordinates, our axes. The other day I went to the optometrist. I had my annual eye exam, and one of the tests that they did had a little star shape, and it kind of looked like that, and that it happened to move around or something, and I couldn't help but seeing an X, Y, and Z axis. And it was one of those where if you look at a drawing of a three-dimensional object, and sometimes it looks like it's situated one way, and then it kind of pops around and it's situated the other way. It kept doing that also. So anyway, Y. So we have this elliptical cylinder along the y-axis. It's going to be stretched in the which direction? Which is going to be the major axis along? Y? The major axis is the Y? The time axis, the imaginary axis. All right. So which axis is going to be our major axis? X or Z? Z. Okay. So our ellipse. Our ellipse is going to be stretched along the z-axis. So if I sketch this in the xz plane, there's my cylinder. Not a bad cylinder this time. So there's my elliptical cylinder, and my curve is going to lie along the cylinder. So as t increases, as our parameter increases, it's going to move along the y-axis kind of in a linear fashion. So what kind of motion is going to happen? Dylan's doing this. It's going to spiral around this cylinder. So it's going to do something like, let me draw the curve. It's going to do something like this, and it's going to go around behind here, and then come back in the front, like so, and spiral around that cylinder as t increases. And we call this shape that does that kind of spiral shape, that's a helix. So we would call this curve an elliptical helix. Helixes show up a lot. We will get to the point where we'll look at this vector value function and we'd say, oh, that's a helix. And I have a nice 3D that we can move around. So there's our helix. There's our ellipse in the xz plane. And there's our spiraling along as t increases. And ellipses, we get lots of nice, interesting things happen with ellipses. So there's our ellipse. There's our surface, or our vector value function, sketch of our vector value function. Questions on that one? All right, this is my favorite one from this section. Oops. We want to. Oh, wait, I have some questions for you before we do this this next sketch. These questions, true or false?
True. Maybe. Hey.
Because we're in calculus, not in logic, we can't just answer yes. True or false? Yes. So I'm going to say if f, g, and h are first degree polynomials, then the curve we're given by x equals f of t, y equals g of t, and z equals h of t is a line. So we have this, we could make a vector valued function, and all of our component functions are first degree polynomials. So each component is linear. So I heard a few truths, a few falses. So let's go a little further with this. If f of t is a first degree polynomial in t, how could we write some first degree polynomial for x? How would we write that as x as a first degree polynomial? X equals nt plus b, okay? Some arbitrary constant times t plus some other arbitrary constant. It's like y equals mx plus b. X equals nt plus b. How would we write y? We'd end up with a lot of letters, right? So we could say mt plus c. And we could do the same thing for z equals mno ot plus d. What could we start with? Yeah, we had n, m, o. I was trying to be orderly, sort of. So here are our parametric. Here are our parametric equations. What does this set of parametric equations describe? OT. What kind of curve do these parametric equations describe? This is a line. These are parametric equations for a line. So this is a line. So this is true.
Line factorial?
Line factorial, yes. Because we're in 3 dimensions.
Oh, factorial.
All right, so now we're going to go the other direction. We're going to talk about the converse. If x equals f of t, y equals g of t, z equals h of t is a line, then f comma g comma h are first degree polynomials. All right, so we got falses really quickly. What would be a counterexample here? They could all be secondary, so we could say the one I picked. I went even further. I said x equals e to the t, y equals e to the t, z equals e to the t. So same kind of idea. So this is false. False. All right, next one. Do you like true or false? Should we have true or false questions on our tests? All right, so we have 2 objects for this one. And they're traveling along the curves ti plus t squared j, and u of t equals 2 plus ti and atj, and we want to know I'm saying that these two objects will collide. We want to know, is that true or false? We had someone brave say true. So in order for them to collide, what would have to be true? Their components would have to be equal. So what would that imply? For the x component, that would imply that t equals 2 plus t. For the x components to be the same. And what does this tell us? If I solve this, what do I get? 2 equals 0. Can we ever have that?
You can make it work.
We could make it work. We'd have to move along the imaginary axis to be our major axis of our ellipse. So this is going to be false. Our components would have to be equal in order for these to collide, so this is going to be false. Last one. Last true or false, and then we'll sketch another curve. So we have r of t. T squared I plus t sine t, this one should be easy, j plus t cosine t k. This lies on the paraboloid. X equals y squared plus z squared. We want to know if that's true or false. This is kind of like the last example we did. True? So we want to see does x equal y squared plus z squared. So let's do y squared plus z squared. Y squared plus z squared equals t sine t squared plus t cosine t squared. And what does this simplify to? T squared. T squared is x. So x equals y squared plus z squared. True. So this vector valued function would lie along on the sides, on the outside, on the surface of a paraboloid. So that would be it. So it would be somewhere on the surface of a paraboloid. Aren't these kind of fun? I love thinking in 3 dimensions. All right. So what we want to do next is, if we're given some kind of arbitrary curve, and we'll do it for now, we'll just do it in the plane. We want to write a vector valued function for this curve in the plane. So we're given some kind of curve or some kind of sketch of a curve, and we want to represent it as a vector value function. And then we'll do my favorite example. So we want to represent a graph. And I'm just going to say VVF, vector value function. All right, so we're given this graph, and we're in the plane here. And we're traveling along this graph. And this is at 10, and this angle is 45 degrees. And this curve is x squared plus y squared equals 100. And we want vector valued functions for the boundary of this region. So we're going to write vector valued functions for this boundary. Now for this kind of problem, we don't have to write one vector valued function for the entire boundary. We can make several and just put them all together. All right, so what I'm going to do here is I'm going to call this curve 1, curve 2, and curve 3. So we're going to write 3 different sets of vector valued functions for these things. One vector valued function for curve 1, one for curve 2, and one for curve 3. So for curve 1, this one should be easy. What would be our vector valued function for this curve? I'm going to say r of t. What is y on this curve? 0. So do we need a y component? No. So what's the easiest way we can get from 0 to 10 for our x component? What do we want our parameter to be? How about t? I? How about that?
Why do we put in that interval for t?
Because this curve goes just from 0 to 10. So along this curve, x is varying from 0 to 10. So I'm just going to say r of t is ti for 0 less than or equal to t less than or equal to 10. Pretty easy. For curve 2, what's going to be, we don't have to use t, we don't have to use the same parameterization. So what would be an easy way to parameterize, a familiar way that we've done before, to parameterize this curve? How have we parameterized the circle before? Sines and cosines, right? So let's let x equal cosine t, and we have to account for this radius, so it's going to be 10 cosine t. Y equals 10 sine t. And doesn't this give me x squared plus y squared equals 100? So I'm going to say R of t equals 10 cosine ti plus 10 sine tj. And t is going to vary from what to what for this curve and this parameterization. 0 less than or equal to t less than or equal to, my angle varies from 0 to 45, pi over 4. So that's going to take me along this circle from here up to here. So there's my parameterization for curve 2 and my vector value function for curve 2. Now let's do curve 3. So for curve 3 we have another line. So we're going to have a nice linear relationship between x and y. What is that point here? What is x and y up here at when theta equals 45 degrees? We need to figure out that point so we can write the equation of the line. 5 root 2. We can plug in t equals pi over 4 to get x and to get y. So this is going to be 5 square root 2 and 5 square root 2. That's going to be this point. So we need to write a linear equation that takes us from 5 square root of 2 back to 0. So R of t. So what's going to be a nice, how can we get from 5 square root of 2 to 0 with a vector value function? Where do we want x and y to start out? What coordinates do we want for x and y? 5 square root of 2. So that's a good place to start, right? 5 square root of 2, and I'm going to put an I here, and a plus, and a 5 square root of 2, and a j here. So how are we going to get from 5 square root of 2 back to 0? What's the easy way to get back to 0? T. I'm going to say, how about 5 square root of 2 minus t and then 0 less than or equal to t less than or equal to 5 square root of 2. That's the easiest one I can think of. That takes me from here to here. Start with the point that I want, subtract my parameter, let the parameter start at 0. Now this isn't the only way that we could do it. There are other ways we could parameterize these curves and come up with the same thing. So this is just the first idea that I came up with. So when we have a curve, when we have some kind of boundary, some kind of curve that we want to represent as a vector value function, pick your easiest parameterization, and just make sure that your parameterization takes you where you want to be. A lot of times the problems will be given and they'll say use such and such as your parameter. So they give you a hint. You don't have to come up with the parameterization. They give you a hint as to what the parameterization is going to be. But here, because we have lines and circles, those parameterizations are pretty easy. All right, questions there? So if we put these together, we would make a kind of a piecewise function, and we put together these three curves, these three r's, r of t, and that would be our vector value functions for the boundary of that region. All right, my favorite example. Sketch this curve. of intersection of x squared plus y squared equals 4 and z equals x squared, and then represent the curve with a vector valued function. And we'll be nice here and give you the parameter. X equals 2 sine t is going to be our parameter when we write our vector valued function. All right, so we need to figure out what these two surfaces are. These two surfaces are going to intersect somehow, and where they intersect is going to give us some kind of curve, and we want to sketch that curve, and then we want to represent the curve with a vector value function. So x squared plus y squared equals 4. What is that curve? What is that surface? Sorry. Circle in the xy plane. So in 3 dimensions we get a cylinder. This is a cylinder. And what's the axis of our cylinder? Which z. Cylinder along z axis. So let's sketch that. There's going to be one surface going to be a cylinder along the z axis. So that one's not too bad. See if I can do a decent sketch here. Make it a little bigger. So there's our cylinder. And I'll extend this back this direction so we know that we're going back here as well. So there's our cylinder. Now how about z equals x squared? What is that going to give us? We get a parabola, or traces a parabola in which plane? XZ plane. So our surface in 3 dimensions is going to be what? We're missing one coordinate. We just talked about this one. We're missing one coordinate. So our surface is a cylinder. And the trace is a parabola, so we get this parabolic cylinder. And we've talked about this one before. It kind of looks like a trough. So this is a parabolic cylinder. So we get parabolas or traces of parabola in the XZ plane. I'm going to draw the parabola out away from the XZ plane first, because our cylinder extends along the y-axis. So here is our parabola. In the parallel to the XZ plane, and this parabola is going to come along here and intersect this cylinder. So the way I visualize this one is I think of this parabolic trough, this cylinder, kind of slicing through the cylinder along the z-axis. So as it slices through, let me see if I can sketch this curve. we're going to get a curve that looks like this. So as it comes along on this side, the side of the paraboloid, or the parabolic cylinder, is going to intersect the cylinder here, and then it's going to curve down along here. The same thing along that axis, and then back behind here is going to come up like so, and it'll curve down behind again where the cylinder cuts through here. So I thought of this parabolic cylinder slicing through the other cylinder. So our curve, this is a rough sketch of our curve of intersection. It's kind of almost like a sine curve stretched around that cylinder. So to help us visualize, I did two things. One, I made a model. So I'll pass that around. And I also did this in, made a graph that we could rotate around. So this cylinder cuts, this parabolic cylinder cuts through this other cylinder. So let's take a look at that one. And this is where this software that you have will be very helpful to help you visualize this. There's a picture of it. So there's the parabolic cylinder cutting through the other cylinder along the z-axis. And in dark blue there is our curve of intersection. So I think that was how I visualized it. How does this parabolic shape slice through this cylinder? So we look at it straight on here. We get a parabola here, and along this side, because it's rising up, we get a kind of an upside down parabola. It's cutting through there. So there's kind of what we drew, a much nicer looking thing than what we drew. And then this curve itself, we'll write the curve, and then we'll write the parametric equation for the curve, and then we'll show I made another graph that shows just the curve without the surfaces there. All right, so there's a rough picture. The Mathematica picture is much nicer than my sketch, but sketch turned out pretty close. All right, so now let's represent the curve with a vector value function, and our parameters x is 2 sine t. So if x is 2 sine t, we need x squared plus y squared equals 4. So how are we going? What's going to be our parameter for y? To get x squared plus y squared equals 4. 2 cosine t. And that will give us x squared plus y squared equals 4. And if z equals x squared, what's z going to be? Z equals x squared, what's x? 2 sine t, so z is going to be 4 sine squared t. So this part's easy. Our vector value function for the curve of intersection is going to be r of t equals 2 sine ti plus 2 cosine tj plus 4 sine squared t. Okay. And that would be a vector value function for this curve of intersection. That one's not too hard. And they gave us the parameters, so that made it easy. So let's take a look at a sketch of just the curve, so without all this surface stuff in the way. So there's our curve. And that's our vector value function, 2 sine t I, 2 cosine tj, 4 sine t squared, 4 sine squared t k. And there's our curve. There's our parabola cutting through the cylinder. It's because I did this, it stretched a little bit, so rather than a circle, it looks like an ellipse. But there's our curve of intersection. And a nice vector value function that represents that curve. I just love doing this. All right, questions? I just want to. And when I made this one, I was really excited that this one turned out as well. So I just wanted to look at it again. I kind of like it this way with the line showing like that. All right, so today's homework is all this kind of sketching, visualization, things with these vector value functions.